If you were to predict which spots would be modified, it would be the OH group would favor the purple orthocarbons. The alkyl donating group would also favor the blue orthocarbons, those that are ortho to the alkyl group. And of course, the strongest donor would win. The electrophile in making diiodotyrosine is this weird, I'm not sure how to say that, hydroxyiodide, I don't know. In any case, what happens is your body uses hydrogen peroxide and an enzyme and then iodine, and this is why you want to take iodized salts, because it's a source of iodide in your diet. Body can modify that to be an electrophile, which then can be attacked. You've got a weak bond between heteroatoms. The nucleophile attacks to make a new carbon iodide bond. Then you get this intermediate where a base restores aromaticity, and then finally you get this precursor to the thyroid hormone. And there's more steps downstream, but this is the one that installs a key carbon iodide bond. Right. So just a couple of examples. Whenever I show stuff like this, people want to know, it's sort of a trade-off, right? I want you to pay attention to it because it's kind of cool. On the other hand, I don't want you to be freaked out by it. So walk the narrow ridge between those two alternatives. You don't need to memorize everything, but you should also not ignore it. Understand the similarities between what I've shown you and the basic mechanisms we've learned for electrophilic aromatic substitution. Okay, now I want to tell you the story of textiles and the color purple. So later on this year in Come Follow Me in Acts chapter 16, we're going to read about a woman named Lydia in Philippi where she met Paul and Silas, and she's called a seller of purple. And at the time, that sounds kind of funny, a seller of purple? A purple what? No, of purple dye. At the time, one of the main sources for the color purple in terms of dyeing clothing was a Mediterranean sea snail. So you had to dive to the sea floor and recover these creatures and then grind them up and extract the purple coloring from them. That was pretty expensive, and because of that, purple was the color of kings and emperors, the elite. The molecule that is probably the one responsible for Lydia's career is this one. It's called Tyrian purple, probably named for the Mediterranean city Tyre. Oops. And it looks like this. It's a highly conjugated system, as colorful molecules tend to be. The more atoms you have involved in conjugation, the smaller the gap between HOMO and LUMO, and you can get it so that visible light photons can promote electrons through that HOMO-LUMO gap, and then your molecule absorbs in the visible region, and what it doesn't absorb, it reflects, and that's where you get the color from. So this was very, very expensive, which is why it was not a very common color in modern in clothing up through the 1800s. In 1856, an 18-year-old William Perkin had a lab in his house, because this is, I guess, what you did when you were British and were fairly well-to-do. And he was trying to make a molecule called quinine, which is an anti-malarial. And he was trying to do this by mixing together aniline, which is this benzene ring with a nitrogen, but his sample of aniline was contaminated with these related molecules, amino these related aminobenzenes that have also methyl groups on them. We've gotten a lot better at chemical separations now. You could order aniline from a chemical company and they would provide it for you in a lot of purity, but right now, or back in Perkin's day, probably the best they could do for separating things was distillation, and depending on how close the boiling points were, you might get a mixture of things. So he was trying to make quinine, which I should have shown you the structure to. I guess we can look it up. Do we dare? Quinine. Yeah, not totally sure. Of course, this was also before the days of high resolution structures, so it's not totally clear how he thought he was getting that out of his starting materials. But in any case, thought he'd give it a go. Instead, he got what often happens when you don't know what you're doing. He mixed sulfuric acid and potassium dichromate. This is an oxidizing agent. It's a reagent you may be encountered in 351. But he got the sort of black tarry solid at the bottom of his reaction flask, which usually means, okay, you failed. And instead of throwing the flask away, he decided to try to clean it out. Sometimes when that happens, we call it a loss and we just say, okay, I'm not cleaning that out. We'll just have a memorial service and on it goes. So he attempted to rinse the flask out with alcohol, and the liquid turned purple. And being 18, naturally he thought international textile color industry when he saw the color purple. So he, a whole series of events ensued. He learned to use that to dye silk and textiles. He patented it. The next year, as a 19-year-old, he opened a factory. He was 18 in 1856. 18 years later, at the age of 36, he retired, a wealthy man. You can still, there are still samples of his original dye that are available. And some of them may actually be in your, well, let's actually look it up. I'm not sure if it's in your text, but we'll, Movine. So this is some silk that had been dyed with, that's still not any better. Yeah, silk that had been dyed with the stuff that he made. And there may be some details in your text about this, but he called it Movine because of the color purple, I guess. And this led to a surge of research in organic chemistry for making all kinds of things, not just dyes, but things that had other interesting properties. Here is the structure of Movine A. It turns out his molecule, his dye, is actually a mixture of multiple highly colored compounds. We won't worry that much about the mechanism for making Movine A, even though it does involve electrophilic aromatic substitution. If you look, you can see within this structure, first you can see that it's highly conjugated, right? Follow through the atoms and you've got Sp2 hybridization all along the way, aromatic. All of these groups are conjugated with each other. And then you can see that the orthomethyl contributes to this portion of the molecule. The regular aniline is the orange portion, and then in green you have the orthomethyl aniline. And you can see along the way we're making some bonds. I've highlighted in red the bonds between these individual subunits that had to have been made. And you can see their bonds between aryl or aromatic sp2 carbons and some other group. And so it turns out that these bonds were made via electrophilic aromatic substitution. I'll show you one example. I don't want you to worry about it. The process involves single electron oxidation, which doesn't make a lot of sense, and we haven't learned about it. You basically need that to convert some of these molecules into electrophiles. I'll show you one step. Ignore this. This is the oxidation, but here is an electrophile, and a nucleophile can attack at the nitrogen. You probably don't need to worry why this could be an electrophile. That's beyond the scope of what we want to do. But the idea is that the aromatic ring can attack the electrophile via an electrophilic aromatic substitution. These two arrows are mostly to explain the donating effect of this nitrogen on the ring. But pi electrons involving the paracarbon are going to attack the electrophile to make a new bond, and then a base will remove a proton to restore aromaticity. So this, and this happens again and again. That's just one of the bonds that get made here in red. But that happens again and again until you have the full Movine structure. And there are a few other isomers that are included. I don't know why, that was, you can ignore basically all of that. That's just me sort of trying to explain to myself how it happens. Okay, so electrophilic aromatic substitution used to make the color purple. But as I said, that started a whole industry in dyes and textiles. And particularly in Germany, they quickly learned to make a class of compounds called azo compounds that had interesting properties as dyes. So we're going to learn actually how to make azo compounds, but before we do that, I want to show you a few of them that are colorful and then tell you the story of how those colorful molecules led to the concept of chemotherapy. So all azo compounds have in common a doubly bonded nitrogen, two nitrogens doubly bonded to each other, and they will differ in the identity of the groups attached to either nitrogen. The one here, this is just FYI, don't intend for you to memorize this structure. This is called para-red, and it's red. And basically, we're going to learn how to make both of the bonds that I'm highlighting in red. There are another that you may occasionally have heard of. It's sometimes used, I think, as an indicator, is called Congo red. And this is a weird one. You've got two different azo groups linked by a same central, what's called biphenyl linker. And then on either end, you have these two benzene rings, and you have, let's see, SO3 minus, NH2 here, and an identical benzene ring on, or aromatic ring on this side with an NH2 here, and an SO3 minus here. That's Congo red. The bonds that we make in this process I'm highlighting here in red. And you're going to see as we learn how to do this why there was such an explosion in research in these molecules, because they're very modular. Do you see if you'll see that it's pretty easy to make both of these bonds, which means this is basically Lego type chemistry. You can click different pieces together and you can try them in multiple combinations. So it's really easy, for example, to keep one side of this constant and then try everything you can think of on the other side, or vice versa. That's called combinatorial chemistry, and that approach persists today in drug discovery. And the concept is something called structure-activity relationships, or SAR. The idea is that as you change the structure of a molecule, you change its properties, and so you just vary the structure until you find the property that you want. And of course, they did this. The property they were looking for was color. At about the same time as this explosion in research into dye molecules was happening, German chemist Paul Ehrlich was working with dye molecules to stain bacteria and histological samples. So what do we mean by that? Tissue samples. When you look at slices of tissue under a microscope, they're not colorful, they're basically transparent, and so sometimes you need some help visualizing what's going on there. And people had been looking now with all of these colorful dye molecules, well, let's just wash our tissue sample with one of the dye molecules and see what happens, see if that helps us visualize some things. He had been working with a number of different samples, one of which was a dye, and it's not an azo dye, but I'll draw it for you. It's called methylene blue. And he noticed that this would stain selectively a particular Plasmodium parasite. And that led him to the idea, well, if the parasite selectively is stained by this dye, if I administer the dye in large enough amounts, can it kill the parasite? And by stain, what do we mean? Well, first you would wash the dye on the sample of a cell, and then you would rinse the sample out, and the cell or parasite would take up the dye into itself. And so that led to the idea, that cell or that parasite is binding that dye and not releasing it. So it's almost like I've just targeted that cell with some molecule. Now, can I also kill that cell? Because naturally, I don't know how old Paul Ehrlich was. I guess this is Perkin, but one of the, well, can we kill it? And it worked. It actually targeted the parasite and killed it. And this led to the idea of chemotherapy, which is, can I have a molecule that binds a particular kind of cell that I don't want to live and kill it? That's the whole concept of cancer chemotherapy. Can I selectively interfere with the growth of a cancer cell in a way that doesn't kill non-cancerous cells? And so thus was born the concept of chemotherapy. I'll show you a couple of azo-type dye molecules that have been used, not necessarily for cancer, but for killing bacteria or parasites. The one that I'll draw here is very similar actually to the Congo red. It's called trypan red. And again, I'll have you compare the structures, and you'll sort of get an idea of what the chemists were doing when they were messing with these molecules, see what's different. And the differences you observe are going to be because some guy said, let's try this. So this is similar to, let me pull Congo red down a little bit closer so you can see the similarities in structure. It's got the same sort of biphenyl core, only this time they decided to play around with that biphenyl core a little bit. They put a sulfate group on it, on either end, they still have these two benzene rings. Two benzene rings fused together, by the way, are called naphthalene. I got that wrong, didn't I? Okay, so you can see that now they've got, they've put the amino group here instead of here, and they put an extra sulfate group on the naphthalene ring. Same thing over on this side. Okay, that's trypan red, and are you tired of drawing it? I am too. Again, notice the modular structure. We're going to make those bonds between the benzene rings and the nitrogens. So they're literally mixing and matching pieces and adding different things. Trypan red is actually used to kill a certain kind of parasite called a trypanosome. And you can Google that, but that's associated with some sort of subtropical types of diseases. I think Professor Ken Christensen in our department is working on some trypanosome type diseases, but this was one of the early azo dyes, and to some extent this was, let's just try everything, and gee whiz, this dye that's red also kills parasites. And you could ask, and I don't know actually the mechanism, how does it kill the parasite? How does it get inside the parasite? Why does it stay there? I don't think they knew any of that at these early stages, other than the dye molecule binds the parasite, it selectively labels the parasite, stains the parasite, and it kills the parasite, so yay. But that led to all kinds of research, because that's what we call a lead. I don't know. We should read about that. I don't know how it was administered. Orally is probably probably the best guess. Let's see. So we're going to learn how to make azo compounds, and that's our starting point is going to be with the same starting point of Professor Perkin, which is, actually I don't know if he was a professor, Mr. famous chemist Perkin, British chemist Perkin. We're going to start with aniline, all right? So here's the chemistry you need to be able to do. Of course, where do we get anilines from? You get them from benzene. Via the electrophilic aromatic substitution reaction. Aryl nitration is how you put a nitro group on the benzene ring. And then, as you learned last time, you can reduce that nitro group using hydrogen and palladium on carbon to get aniline. All right, so that's aryl nitration followed by reduction to get the aniline. The next process we're going to do is called diazotization because we're going to make what's called a diazonium ion. We start with the aniline, and then we're going to use a new and unusual reagent you haven't encountered before, sodium nitrite, That's different from nitrate. Nitrate has 3 oxygens. Nitrite has 2. And you need acid. And this will convert the aniline group to the following molecule, which is called a diazonium salt. The salt is because you've got the counter ion. This portion is diazonium. So I remember learning about this when I took this class in the spring or the winter semester of 2001. And maybe it was that I was engaged to Amber at the time, but I promptly forgot this. So there is a mechanism that's known. I don't really care that you know it, but I think I'm going to show it to you just so that you have some concept of what's going on. I realize it's a toss-up whether you'd rather see stuff that's not important so that we can kill class time without introducing concepts that you're vulnerable to on the exam, or whether you'd prefer me to just focus on the essentials and leave out the non-essentials. But it's my class, so I can do what I want. I think... What's that? That's what I say to my primary kids. I don't care what you think. It's a wonderful thing to look into the eyes of a child and tell them you don't care what they think. I'm sorry, I'm not that big of a jerk. My primary kids heckle me, by the way. All right, so what's going on here? Well, let's draw first the structure of nitrite. Okay, that's the nitrite ion. We're in acid, so you should be able to see how it would be pretty easy to make that, nitrous acid. Maybe you saw that before in general chem. Hono? And then having made nitrous acid, you could maybe see how you could also protonate that oxygen again, thereby converting it into a good leaving group. And at that point, we can do carbonyl-like chemistry, have lone pairs on this oxygen kick off water as the leaving group. And that gives us what's called the nitrosonium ion, which is an electrophile. And what happens next is basically just nucleophile attacks electrophile. The aniline lone pairs attack the nitrogen, and we're basically going to do carbonyl type chemistry. I think that's right. All right, so that's an intermediate. Now, except we lost all the double bonds in the benzene ring. Now, if you compare what we're doing here, what we've got here with where we need to end up, we're clearly going to get rid of water, right? Because the oxygen's gone, and we got to get rid of these hydrogens. Basically, we're going to do tautomerization reactions to move the hydrogens from this aniline nitrogen out onto the oxygen until we get to the point where the double bond is between these two nitrogens and you've got water out here. Okay? So, again, this is just for your FYI, not your That doesn't make any sense. Any of you guys ever watched the show The Middle?
Yeah.
Yeah. I remember the son Axel, who's not the sharpest knife in the drawer, says, FY your information. All right, so we're going to get rid of that proton. Of the 3 Heck children, though, I think my sons have identified most with Axel, so I don't know whether I need to be worried about that or not. Okay. Then, having done that, you can see how you could draw a resonance structure where there would be a double bond here and a positive charge on that nitrogen and a negative charge there. Yeah, so that means that we ought to be able to put a proton on that oxygen. And then we could draw a resonance structure where the double bond was here and the positive charge was there, and that was just a neutral oxygen, right? Then we could remove this proton to create a neutral nitrogen. Then we could add a proton there. Then lone pairs kick down and water leaves. And that gets us to the diazonium salt. So I realize that's incomplete, and if I think too, I'll write the complete mechanism in the notes, but it's not anything you need to memorize or study. I just want you to have seen it so you have an idea of what's going on. Okay. So it turns out this process works not only for aryl amines, but it can also work for alkylamines. The problem is that if you do this with, say, an alkylamine, the diazonium group is basically the best leaving group ever. It's nitrogen, right? And we're swimming in an atmosphere of nitrogen that's sitting around and doing nothing. Best leaving group ever. So for alkyl diazonium salts, it turns out they lose nitrogen and just become the carbocation and then do sort of carbocation type chemistry. In contrast, you've learned before that having a positive charge in an sp2 type orbital, for example, a vinyl or aryl carbocation, not a great thing. So the aryl diazonium salt is actually quite stable. It doesn't lose nitrogen, which is kind of cool. All right, so having made the diazonium salt, what can you do? Because our focus today has been on azo compounds, I'm going to show you how you can use the diazonium salt as an electrophile to make an azo compound. But there's other cool things you can do with it too, which we're going to talk about. All right, so coupling of diazonium salts with arenes. By that I mean other aromatic compounds. So here is a diazonium salt that's an electrophile. Oops, that's not the right place for the positive charge. That one is. And then we're going to use some other benzene ring as a nucleophile. So let's just use maybe a phenol or something like that. Based on what you learned in the previous chapter, the OH group is an electron donating group via resonance. And that means that it's going to favor ortho and para substitution. We'll draw the para product, but we would get a mixture of ortho and para, and that's fine. Here's the mechanism. Pi electrons from benzene, attack the nitrogen of the diazonium salt. Maybe we'll just draw it to there. and then one of the nitrogen-nitrogen pi bonds breaks to get rid of the formal charge, positive formal charge on that nitrogen that's attached to the ring. When that happens, here's the product. Nitrogen goes from sp hybridized there to sp2 hybridized. As we saw before in the previous chapter, we used to have a hydrogen here. When we attack and make the new carbon-nitrogen bond, we've broken aromaticity, but we can restore aromaticity by removing some proton. I'm not saying what the base is because you do not have to add any base to make this reaction work, to make this reaction go. Whatever is in the reaction is sufficient enough to act as a base to remove that proton. And when you're done, you have now your azo compound. Okay. So that's coupling of the aryl diazonium salts with other benzene rings. So let's think about a synthesis now. Well, I'm going to draw a diazo compound for you. That would be, I'm not sure what color it would be, but it's starting to look similar to some of the things we've drawn previously. Okay, make that. How would we do that? You just go into your basement, you mix a bunch of stuff together, and you hope for the best. Pretty much. All right, first thing we need to decide is what bond should we make last? Do you want to put these functional groups on last, or do you want to do the linkage last? That's good instincts. Why would you want to make the linkage last? If you waited until you had something like this before you start to try to install those other functional groups, what's your problem? Sorry, that's what's your problem? What's the problem with trying to install just whatever, a sulfur group here? Yeah, you go on either one. You got some selectivity issues. So here's a big thing in synthetic strategy. If you can, get functional groups in place first and then couple things together. That makes your life a lot easier. It's called a convergent synthesis approach. It makes your life easier because you don't have to worry about late stage selectivity. Well, how do I get one group on this side versus the other side? If you can avoid that situation where you're having to, how do I be selective for one benzene ring over another, your synthesis is going to go a lot smoother. So I agree with you. So we want to make one of these two bonds as the last stage. Now go back and look at the coupling of diazonium ions. This is our electrophile, and this is our nucleophile. So tell me, oh, we need to get rid of that, right? What do I have two? There we go. Tell me which portion of these two rings do I think should be my electrophile and which should be the nucleophile? Let's look at those substituents. What kind of substituent is that? That's an electron donating group via resonance. Whereas here is an electron withdrawing group, also via resonance. Ideally, I would want to choose my nucleophile. I'd want to choose my nucleophile such that it's the electron-rich one, right? Do you remember we learned last time that some groups activate rings relative to benzene, make them react faster. Other groups make their benzene ring react slower. The nitrogen here is a donating group via resonance. There's the lone pair. We want something that's going to make it a good nucleophile. So yeah, I'm going to propose then that this side be my nucleophile and this side be my electrophile, which would mean the nucleophile piece is simply going to be, by comparison to what we did before, that. What's my electrophile going to be? Going to have the benzene ring, going to have the sulfur group, and what else? Okay, that diazonium salt that we just learned how to make. Okay, good. Now you've got two simpler synthesis problems now. And it's good to pause at this stage and ask, if I mix this with this, would I get this? And the answer is yes, if you follow that mechanism, that coupling mechanism we did before. So now it's a review. How do I make, my allowed starting material is benzene. So how do I make that dimethyl aniline from benzene? Forget about the methyl groups. Do I know how to make something like this? Yeah, I just showed you how to do that, right? That's the nitration to give you the nitro group, followed by those new, palladium catalyzed reduction of nitro to aniline. Then what do you think? How do I get that to work? Probably the best I can do is just an SN2 type reaction. Probably I just want an alkyl halide. If you're thinking about the deep past and modifying amino groups with alkyl halides, one of the problems we worried about was over alkylation, because you add one group and you now have an amine that's more nucleophilic than the starting material. Anilines are a little bit different. There's not a huge push to go beyond this point because those lone pairs are tied up in resonance with the benzene ring, so that probably would work. Okay, let's go ahead and take a break. I want you to be thinking in the meantime how you would make the diazonium salt. So go ahead and take a few minutes and we'll pick it up again around 9. All right, let's now talk about how you make your electrophile. And we're going to make it from benzene. Let me just say that students kind of want to know, what is this diazonium group? Is it an electron withdrawing group or an electron donating group? Based on the fact that you have a pi bond between the thing that's attached to a ring and an electronegative atom, and because this is a positive charge, probably this is an electron withdrawing group. I can't think of really any examples in your text where it takes a molecule that already has the diazonium in place and then does other reactions after that to put stuff at these other carbons. Instead, what's usually done is you get all the functional groups in place and then you make the diazonium ion. Probably that's because this is electrophilic enough. I don't know. It's either too sensitive a reagent or it may be deactivating enough to the benzene ring that it's hard to do other reactions once that diazonium molecule's in place. So that's one sort of potential hint. The other hint here is the para relationship between those two groups. This group, as we've said, is an electron withdrawing group via resonance. So if we put that group on first and then attempted to get a nitrogen at someplace else on the ring, do you see what our problem would be? Put that group on first and then what? You get the meta, right? So that tells you that you've got to take a slightly different approach. So it may also be helpful to think backwards just one step and remember that we get the diazonium ion from the corresponding aniline. Okay, and that's that new set of reaction conditions, sodium nitrite and HCl. Now this becomes a problem from a previous chapter, which you should know how to do. Which of those groups am I going to want to go on first? Okay, got to get the aniline in place first so that when we add the sulfate group, it goes on para instead of meta. So you do the nitro, then you reduce from nitro to aniline, and then now that I've got an electron donating group that's an ortho and para director, now I can do the aryl sulfonation conditions to give me the sulfonic acid group. All right. Does that sort of make sense? Yeah. Can you assume that it'll be deprotonated? Yeah, there's no secret or anything meant by that. Your text shows that as a product. If you were in water, that would be just based on pKa. That would probably be existing in its conjugate base form. Yeah. Okay, good. So those are the azo dyes. Anything you want to do? Coupling of azo compounds. There's a few other things you can do with diazonium salts that allow you to make molecules we've not been able to make via any other method before. So that's maybe worth talking about briefly. It also allows us to introduce a new mechanism for aromatic rings. So we'll call this substitution reactions of diazonium salts. So here's a simple aryl diazonium salt that we've just learned how to make. You can actually do substitution chemistry where you replace the nitrogen on your diazonium molecule with a nucleophile. Ta-da, substitution. Now, the mechanism is not SN2. Instead, it's something called nucleophilic aromatic substitution. And this can happen anytime you have, this can happen when you have an electron poor benzene ring with a good leaving group on it. This is a new mechanism, and fortunately, I think actually nucleophilic aromatic substitution is really common in the pharmaceutical industry. It's a reaction that's used all the time. This is going to be the one example of the mechanism that we'll learn about. What happens is that the nucleophile attacks the benzene ring at the carbon that has the leaving group. You get an addition reaction first. This is almost like carbonyl chemistry. And you can see that it would help the reaction go better if I happened to have electron withdrawing groups positioned at the ortho or para carbons where they could stabilize that negative charge via resonance. So, final exam question, which atoms share the negative charge? And there they are. So you get first, the first step of the mechanism is addition. And again, if I had, say, some nitro group here, it would be possible for me to delocalize this negative charge further. So you can favor nucleophilic aromatic substitution reactions if you put withdrawing groups at the correct positions in this ring. However, we have destroyed aromaticity, but as with carbonyl chemistry, we can ask ourselves, do we have a good leaving group on the carbon that's tetrahedral? The answer is yes. Electrons kick down and kick off nitrogen. That restores aromaticity. You lose nitrogen as a gas, and you're left with your substitution product. So we replaced this nitrogen as a leaving group with this nucleophile. Okay, so that's the first time we've ever made phenol. Now you know how to do it. Notice how sort of convoluted that reaction series would be. Nobody would actually do this. We would just buy phenol because it is cheap. But if you were required to do this, say on a question where everything had to start from benzene, you'd start with the nitro, you'd reduce to the aniline, you would diazotize, and finally you would introduce your nucleophile to get your phenol. All right. I'll show you a couple others that your text presents. Some of these involve counter molecules and reagents you haven't encountered before. In particular, copper, which your text sort of shows that without explanation. I've never done these reactions before, so I really don't know what the copper is doing. Do you recall that we've learned how to make the aryl halides through electrophilic aromatic substitution in the sense that we know how to do bromo and chloro via this method? You take chlorine or bromine and the appropriate Lewis acid, and we know that mechanism. At the back of your mind, you may have been thinking, well, does it work for fluorine or iodide? And the answer is not that well. But we do have alternative methods for making iodobenzene and fluorobenzene. And it involves this diazonium approach. So if you take your diazonium salt, expanding the page, and you use copper iodide, you can make iodobenzene. Same way through phenol. Achievement unlocked. If you want to do fluorobenzene, you use a different reagent. And this is one that, again, your text presents without a lot of explanation. The reagent is HbF4. And you could ask yourself, why not copper fluoride or F- of some kind? And I don't know. I will draw for you the Lewis structure of HbF4, and you can promptly forget it. That's BF4 minus. HbF4 is that. Fluorine bonded to two things. I'm not really sure what's going on with that reagent, but somehow it delivers F minus to the carbon where your diazonium group is, and then installs the fluoride. So maybe this is kind of like aluminum hydride or borohydride. Maybe this is an F minus delivery agent, but I don't actually know. Nevertheless, the reason I'm showing it to you is because fluorine shows up all the time in drug molecules. And so installing fluorides at specific places in molecules is a highly, highly useful reaction in organic chemistry. All right. So with that, we ought to practice a little bit of synthesis, and then I'm so excited about the next chapter, which is about peptides and proteins, which is what my research is on. But probably, in the interests of your sanity in the exam, we probably won't go there yet today. All right, so let's practice a little bit of synthesis.
I have a quick question.
Yeah, shoot.
So the OH here can't attach to a normal benzene because it's just not strong enough, but it can when there's this other group.
You got to have a leaving group, right? Look at the mechanism. OH can't attach to a normal benzene because there's no good leaving group. You could conceivably, I don't know how likely it is, but you could conceivably make something like that, but what are you going to lose? Yeah. All right, so let's make this one. And you got to start with benzene. And there's a clue. And the clue is in the relationship between the OH group and the chloro group and where they are in space. So take a few minutes and see if you can figure that one out. Diazonium is an electron withdrawing group. However, if you find yourself tempted to do electrophilic aromatic substitution using this as a nucleophile, probably there was a better way to do it. Probably you could have done something and then dealt with the diazonium group later. Here's an abstract of a paper in the journal Journal of Experimental Medicine, 1945. That sounds a little scary. Trypan red when injected intraperitoneally into mice. Do you know what that means? Intraperitoneal injection? Abdominal cavity, isn't it? Yeah. How about if you want to sign up for so you were asking her this is administered orally? Apparently not. Was found to lower the incidence of infection of mice also inoculated intraperitoneally with a neurotropic virus. So first they stabbed the mice with the virus and then they administered Trypan red. Antiviral properties, interesting. All right, you got anything? Okay, what do you want to do first? Okay, so H2NO3, presumably you're doing that because you want to eventually make phenol. All right, so what next? Do I want to proceed all the way to the phenol right away? No, why not? I got to get the metachloro there. Now is the time. Now is the time, right? If you have any warriors, tell them now is the time. Right, our goal now is to put the chloro group in the appropriate place. Nitro is a meta director, so, okay. And then the problem's done, right? I can reduce to the aniline diazotize and then substitute. Okay? Any questions about that?
So that whole thing of being tempted to do it later, would it just throw a chlorine in place and sub out?
I worry about that. That's a great question. What if we had the diazo group in place, the diazonium group in place, and then added chloro? Would we get a substitution product? I don't know, but I think I'm worried about it. The two worries of trying to do, I think some of you were probably trying to think, well, should I, or at least back when my exams were non-multiple choice, plenty of people tried this and argued that it should work, and how could I have known that it wouldn't work? And I think the answer is, first, well, what I always tell students on a non-multiple choice exam, on a free response exam, is the standard is, does your chemistry work? And if you're making up stuff that the text hasn't shown you, probably, unless you can find evidence that your chemistry works, you might actually be in trouble. Why doesn't this work very well? I don't know, other than your text doesn't show it as an option. But if I were guessing, this might be deactivating enough, this is an electron withdrawing group, that the reaction just might be too slow to work. And then you're also right that there's going to be some Cl minus present, and you worry about the potential for substitution products. So I prefer, rather than to invent chemistry, inventing chemistry is the stuff of research, right? Which is good. But it's probably best to not try electrophilic aromatic substitution reactions once the diazonium is there. Or at least that's the strategy your text takes. So yeah, okay, what else? Okay, let's do another, shall we? Let's go on. And again, as you're working on this, feel free to check your notes or the text for reactions that you know. Try not to make up new reagents. There's a way to do this that involves well worked out stuff that we've talked about. Hint, all is not as it seems with this carboxylic acid group. There is a group that converts there is a reagent that converts something else into a carboxylic acid that we learned about. Yeah, you could, if you wanted to, you could put the phenol OH on first and then SN2, the methyl group there, or you could just use methoxide as a nucleophile. Yep.
Using the same method that we put the OH on, right?
Uh-huh. Yeah. You're thinking about KMNO4?
Like, it only needs the benzoic hydrogen and then like the other methyls and stuff.
Right. I've actually never done this, but so I'm just relying on what your text says. But yeah, as long as you have one benzoic hydrogen for KMNO4, it doesn't matter what else is there. They all get broken and replaced with oxygen. Okay, you got an idea where the carboxylic acid is coming from? A clue here is again that these groups are para to each other, which tells you that well, what strategies do you have? Probably a couple that might work.
To make that carboxylic acid, you use the K and O4.
All right, so then it would have been some alkyl group. I mean, it could have been anything as long as it had a benzoic proton. All right, that's KMNO4. Mm-hmm.
If we have the oxygen methyl group and the CH3 and KMNO4, would that turn the OMe into an OH group?
I don't think so. That's a good question. And I don't know that I would know other than by trying it, but it lacks a benzoic proton, so it probably is going to be fine. Okay. Anybody take a different approach? So, okay, then what? So from that one, okay, so you're thinking this one, and that's what, the Friedel-Crafts alkylation? Okay. Yeah, I think that's fine. I think actually you could do it at this point because you've got two donating groups. It probably does, the order doesn't matter anymore. In other words, if you want to install the methoxy group first and then put the methyl group on, you're good. If you want to install the methyl group first and then put the methoxy group on, you're good. I think either way is fine. Right, and then this from here to here is just our favorite, now boring, annoying nitration. Reduce to the aniline, diazotize, and then add methoxy. All right, good.
Could the methyl group be added at any point after the NO is reduced? Like if you did it right.
If you do it right here,
Yeah.
yeah, so it's a good question. Could you do the Friedel-Crafts reaction on the aniline? Yes, I will allow it. There are some practical issues that I'm not actually sure. A previous version of your text actually made a big deal of it. It turns out Friedel-Crafts reactions don't really work well on anilines. Oops, making stuff up. On anilines in part because the nitrogen's nucleophilic enough that it messes with the Lewis acid catalyst. Like what tends to happen is that the nitrogen binds the aluminum, and at that point you never activate the alkyl halide, and so the reaction doesn't work. We're going to pretend like that doesn't matter. So yes, you could, at the point at which you've got an electron donating group, you could add the methyl group. Yeah.
For installing the carboxylic acid, could you do Friedel-Crafts acetylation using ester chloride, and then doing hydrolysis of the
Yeah, let's see what you're proposing, which is a reagent that we've used before. I think so. Yeah, I mean, that's not that, yeah, I think so. I don't know, but I think that would work. So yeah, you're proposing and then hydrolyzing. Yeah, I think that's reasonable. Okay, others? What's instead of yeah, you could put on any number of things here, provided it has one benzylic proton, and then yeah, you get KMNO4, or you get the carboxylic acid with KMNO4. All right. Well, I've done what we wanted to do in chapter, whatever chapter this is. I can't remember the chapter names because we switched editions of text a while ago, but I still am caught in the old days. So this was chapter 22. So we can end here. I'm also happy to answer questions. I know some of you haven't taken most of you perhaps haven't taken the exam yet, and you're stressed about that. So, questions? Or you can go. We'll start office hours here. Feel free to go. Anybody that wants to stick around and ask questions certainly can.